So welcome to this webinar about the California Carbon Report. This is a publication jointly published by the CLF and University of California College of Built Environments. And I'm Brad Banky. I'm from University of Washington. I have a background in architecture. I was the project manager for this report and larger project that I'll talk a little bit about. And I lead a lot of the research at the CLF on embodied carbon tools, data, and methods, and trying to produce resources for designers, practitioners, particularly to lower the embodied carbon of their projects. Today with me is Yang Shen and Matt Roberts, and I'll let them introduce themselves briefly.
Hello, guys. So my name is Yang Shen. So I'm the researcher from the University of Washington. So my background is all about structural engineering, civil engineering, and the integration of the sustainability and data science. So my role in this project is mainly focusing on the calculation, data analysis, and visualization. I will pass to Matt.
Hi, everyone. My name is Matt Roberts. I'm a researcher at the Center for the Built Environment at University of California, Berkeley, where I'm leading all the life cycle assessment, building decarbonization, and embodied carbon research there. And I helped work on the methods development and results interpretation for this piece of work.
So today we're going to take a quick poll just to better understand who's all here and what your guys' background is a little bit, and then we'll talk about what this project and this study was about, why it was important. Matt's going to cover some of the methodology that we used. Yang's going to go over the results. I'll come back as well as Matt with some takeaways, limitations, and next steps. We'll each offer a few final thoughts about working on this study and then open it up for questions. So to kick things off, I'm just going to talk a little bit about where this study came from and why we chose to pursue it. This is actually the first major publication of a larger benchmarking study that we've been running at the CLF. We ran a similar embodied carbon benchmarking study back in 2017 that provided some sort of order of magnitude benchmarks for what to expect the embodied carbon to be of a sample of buildings. However, at the time, it was relying on some data sources and some methods and modeling practices of life cycle assessment that have gotten a lot better in the last 5 or so years. So now there's a lot more tools available to calculate these impacts. There's a lot more design practitioners and other folks doing LCAs of buildings. And there's a lot richer of data sources and information to analyze. So we relaunched this project with a much stronger focus on data quality and standardization. We're going to do a lot more statistical analysis to really try to understand the trends and driving variables of what's driving higher and lower embodied carbon buildings, and produce multiple different kinds of publications, reports, papers, and lots of good things. So this is really the first major outcome of this larger study. And a quick snapshot of how this has evolved. Back in 2022, we ran a pilot phase of this project to just kind of test out how can we collect data, how might we structure a database to analyze that data, and how might we start to analyze it. So after that, we put out an open call for data, largely to designers, folks working on real world buildings who are using LCA tools to analyze their projects. That took a fair amount of time, and I'll talk a little bit more about that in a minute. We then went on to phase 2, which was this California report that looked at both the embodied and operational carbon impacts of a small sample of our larger data set, specifically for California. We are basically done with this kind of phase 2 and now kicking off phase 3. So there's lots more good stuff to come. And I've said the word whole life carbon, I think a couple times now. If you have no idea what that is, basically we're talking about both the embodied carbon of a building, so all of the materials and manufacturing emissions that go into constructing or replacing materials within a building over time, as well as its operational carbon. So all of the emissions associated with running the mechanical, electrical, plumbing systems over the life cycle of the building, you add those two up and you have whole life carbon. It's kind of important because these two things are often not addressed or not analyzed at the same time, at least historically. And that's starting to change, and folks are really interested in this topic of whole life carbon accounting. So what we set out to do was just better understand the balance between embodied and operational carbon over time. We wanted to at least have reasonable estimates of where a whole life carbon intensity set of values, like what are the numbers we're even talking about when we start combining these two together over the study period of a building? And then what are some of the bigger contributors to both embodied and I would add operational carbon, like where are those impacts really coming from and when? And then what are some of the gaps and challenges with actually doing this type of analysis, both within industry practices and also across policy and design practices of how can we make this better or what can we do with this information? And lastly, how do some of these results vary based on the methods that we choose to analyze them? So the report is published. It's actually two different documents of a report, a full technical analysis report that includes a methodology, detailed analysis, some variability assessments, and lots of additional tables and figures. And then a sort of summary of key takeaways. On the right-hand side, the white one, is a little bit more for a policymaker audience, but it still serves as a pretty good summary of the main report for all different types of audiences. All right, so how did we set this up and what did we actually do? I'm going to start with talking a little bit about data collection and then pass it off to Matt. So as I mentioned in those kind of phase diagrams, this project started a pretty long time ago where we knew we needed to collect some data from real world building projects and real world design practitioners. The challenge with doing that currently is that most building LCAs that are being run are run for very different reasons. You have designers that are doing that just to better understand their own internal design practices, or they're maybe following the requirements or guidance of a green building rating system, or maybe they are trying to adhere to some policy language instead of requirements or client requirements, et cetera. Right now, most of those things have different types of modeling and reporting requirements for how you would analyze and assess the embodied carbon of the building and operational. So what we did is start with a sort of user guidance document and a data entry template to get consistent modeling and reporting coming into our data set, which was kind of the first big quality assurance step that we took. From there, a bunch of our data contributors, primarily architects, engineers, sent us whatever information they could. And we then collected all of that, did a lot of data processing, harmonization, and alignment to fix some of those remaining kind of gaps, challenges, and inconsistencies among practices, even to a next level than that first step, and then compiled that into a project research data set for which we could conduct analysis. So that's where the data came from, and this mainly included folks sending us LCA results from LCA tools, and particularly for this study, we were looking at tools Tally, OneClick, and Athena because they could do whole building lifecycle assessment for the full lifecycle stages that we wanted to analyze. They also sent us a lot of project design parameters like descriptions of the building. How high is it? Where is it located? What type of structural system did it use? What sort of physical scope is included in the assessment? So we have a lot of we call it metadata to be able to analyze different aspects of these buildings and compare them in different ways, which is really exciting. From there, I will pass it to Matt.
Awesome. Thanks, Brad. Yeah, so the data set that we got from all the practitioners and data contributors, in total, we were able to look at the carbon impacts from 30 different building projects across the state of California. All of these were assessed using a 60-year reference study period. It's not saying that all buildings will last for 60 years, but it's a standard frame of reference to allow different comparisons to take place. And we modeled all of them assuming that the embodied carbon impacts from the upfront material production were taking place in 2024 as the first year when construction was happening. We're only looking at global warming potential, also known as carbon. So we're not looking at any other environmental impact categories, which are also important. And then in terms of the embodied impacts, the tools that were used by the data contributors were mainly, well, they were Tally and OneClick LCA. And all the models that were produced, all the buildings had to be at least at the construction document stage, if not further along. And a lot of this was focused on making sure that the buildings can be compared against one another. So we had to limit the scope in order to allow for more comparability across the results. So that led to the exclusion of biogenic carbon, exclusion of carbonation, as well as the leakage of refrigerants, and the embodied impacts of MEP systems. Additionally, impacts associated with construction, also known as A5, life cycle stages B1 to B3, which are some use stages, as well as complete B5, and operational water use were excluded, as well as the deconstruction and demolition, and any of the benefits and impacts outside of the system boundary reported in Module D. These were all excluded from the study as well. In terms of the operational impacts, we used annual average energy use from either measured, modeled, or benchmarked sources, mainly focusing on CEC to be geographically representative of the buildings. We modeled grid decarbonization following the Cambium data set for projections to reflect what is actually happening in the grid rather than using a static grid projection. We go into that in more specifics in the report, and if you're interested in that, feel free to reach out to us. Otherwise, definitely go check out that section of the report as well. And then based off the information that was provided, we also excluded the embodied impacts of the PV systems, which is photovoltaics or on-site energy generation, as well as the benefits from the operational energy use from using those systems and generating that energy on site as well. Next slide, Brad. Awesome. So in terms of the physical scope that was looked at for all of the buildings, focused on the structural system as well as the enclosure of the buildings. However, 19 of the buildings also included interiors. So we split out the interiors to be able to look at the contribution of that separately for those 19 buildings. But we didn't want to compare buildings with a broader scope of building elements included to buildings that don't have that full scope. So we wanted to do an apples to apples comparison. So we have a comparison for structure and enclosure, as well as comparisons for structure, enclosure, and interiors. For geographic representation across the state of California, the buildings are in climate zones 2B, 3B, and 3C. All the new construction is focused around like the main population centers of San Diego, LA, and San Francisco Bay Area. The buildings had quite a wide range of scale in terms of size, ranging from 1 to 17 stories above ground, and about 1,500 square feet to just under 500,000 square feet. And 6 of these buildings also included integrated parking structures, which Yang will discuss in a brief second. And then some of the few limitations, which I'm going to go into more detail at the end of this presentation. We had very limited verification of the model completeness. And again, we excluded other environmental impact categories. So there is other impact categories out there beyond carbon or global warming potential. But for this study, we're only focusing on that impact category. So now it's time to get into some of the results and discussion. So I'm going to pass it over to Yang.
Thank you, Matt. So in this section, I will focus more on the result and discussions through all our graphics. So ahead of this, I want to, for almost our graphics, orange color represents embodied carbon emissions, and the blue color represents the original carbon emissions. ECI means the embodied carbon intensity, OCI means the original carbon intensity, and the WLCI means the whole life carbon intensity. So this slide demonstrates the embodied and the original carbon intensity for all the individual buildings categorized by the 4 different building use type, which are the commercial office, commercial non-office, residential multifamily, and other types. So it is clear to see that there were huge variations of the whole life carbon emissions across these 4 different building use types, especially for commercial office and residential multifamily. They have the largest range of whole life carbon intensity compared with commercial non-office and other types. And among 21 out of the total 30 projects, the embodied carbon emissions, including the interiors and including the structure and the envelopes only, are larger than the original carbon, including the electricity and the natural gas. And the buildings with the relatively high whole life carbon emissions, such as project number 22, number 1 and number 24, they both have a higher OCIs due to the great amount of combustion from the natural gas. Next slide. So we can also use the box plotting to demonstrate the statistical indicators for the whole life carbon impacts. So this slide, the left figure shows the carbon intensity, and the right figure demonstrates the embodied and operational carbon contribution to the whole life carbon with the percentage. So for the left figure, it is easy to see that the mean value of the ECI, which is showing with the black cross marker, is higher than the OCI's mean value, but the OCI has the bigger variation than the ECI, and you can see there were several outlier data points in the operational carbon intensity. And for the whole life carbon intensity, there were kind of big variation, which is sourced from the ECI and OCI. For the figures on the right, even within the limited physical scope of structures and enclosures, the main value, on average, the embodied carbon contribution to the whole life carbon contribution could achieve like 60%, which highlights the importance of the embodied carbon. But the variability of the contributions is depending on the specific type of the building. So the prioritization of the embodied and operational carbon reductions may differ accordingly. Next slide. So, and the quantification of the temporal relationship of operational carbon and the embodied carbon can provide more information for the decarbonization strategies and policy development. So the analysis for the timing of the emissions was also included in this study. So this slide demonstrates the median, annual, and the cumulative carbon intensity for all the buildings. So left figure shows the annual part, the right figure shows the cumulative. So for the left figure, next slide, please. We can see that there was a huge spike at the start of the year, which is 2024. This is due to the upfront embodied carbon. Next one. And for the operational carbon, we can see that operational carbon kind of flat over the 60 years, but before the 2050, there were some small decreases. Okay. There were some small decreases due to the greater decarbonization scenario. And yeah, so there was some kind of periodic embodied carbon contribution due to the material replacement. And the last, there's a kind of spike from the end of life impacts. For the figures on the right, it demonstrated the cumulative and median cumulative carbon intensity at the 3 specific target year, which are the 2030, 2045, and 2084. 2085 is the target year of the California near net zero emission buildings, and 2084 is the end of the building service life. It is easy to say that the embodied carbon plays a bigger role than the operational carbon in the near future, but it is noted that our conclusion based on the median values. So for some specific project, the operational carbon still can be bigger than the embodied carbon. Next slide, please. And this slide demonstrates the operational carbon variability based on the two different building energy use type, which are the all electric building showing on the left and the electric gas building showing on the right. So for all electric buildings, median embodied carbon was much larger than the operational carbon. For the electric gas buildings, median operational carbon is much more larger than the embodied carbon. And around 2047, operational carbon can surpass the embodied carbon. Next. So we can also show the embodied carbon variability based on the different LCA or building design attributes. So in this slide, the LCA tool used building used category and primary structural system were included. And it is easy to see that all building attributes tested were statistically insignificant with ECI due to the small data sets we collected. And the future correlation analysis planned in the larger North American benchmark study. Next one. So we also can compare the ECI including and excluding interior impacts for the all the SEI projects, which are the 19 projects here. So we can see that the interiors increased the ECI by 65 kilogram CO2 equivalent per square meter on average, which is kind of roughly 18% increase. And for the resilient multifamily project, the average kind of 25% increase in ECI due to the huge amount of the interiors. Next one. And we can also demonstrate ECI contribution by the life cycle stages. From this figure, it's easy to see that the module A1 to A3 was top contributor, which kind of 78% for all the embodied carbon. And for some certain projects like project number 22 and the number 32 showing the marked by the black arrows. So the module B4 to B5 impacts contribute over 100 kilograms CO2 equivalent per square meter. So the main reason is due to the more frequent replacement of interior materials in the SEI projects. Next one. And we also can demonstrate the ECI contribution by CSI material division. And we can see that the concrete and metals were the top contributors. For the division 3, concrete can achieve 47%. Division 5, metals can achieve like 20%. And the other contributor from the CSI division could also be substantial for individual projects. For example, for project number 13, the division 7, thermal moist partition could achieve the second biggest contributor apart from the concrete. For the project 22, the division wood, plastic, and composite could also be a huge contribution for the embodied carbon. And for the project number 23, the division 9 finishes would be the biggest contributor. So that's all. I will pass to Brad and Matt for the next section. Thanks.
Thank you, Yang. So to start wrapping up a little bit, I'm just going to go over a few of our kind of key takeaways that showed up in that policymaker document, which you can read more about them. But I think the first was maybe kind of obvious that embodied carbon impacts were really substantial. And I don't think we were necessarily surprised at this, but I think we were a little bit surprised at how substantial they were, given that for most of the analysis, we were really only looking at the structure and enclosure of these buildings. So that was pretty interesting. And the second, that how significant the timing of emissions was. So for I can't remember the exact numbers, it's in the report, but for most of these buildings, the embodied carbon impacts by 2045 were really, really significant compared to operational. And again, there were gaps in some of our data and some of our methods, but it was quite significant at how important targeting embodied carbon can be for near-term decarbonization goals, building designs, policies, et cetera. Lastly, or third, not lastly, throughout the paper, we make the point that it's really important to reduce operational energy demand and reduce consumption. However, what became really, really clear was the biggest driver of operational emissions across our data set was definitely those projects that relied really heavily on natural gas. Now, we didn't have enough data to really analyze like why they had more natural gas or how they might be able to eliminate some of it, but it was really clear that those projects that depended heavily on fossil fuel combustion in buildings were some of the highest emitters. So when we think about electrifying, everybody talks about electrification. Yes, that's important, as is reducing total energy consumption. But electrification without grid decarbonization really doesn't work out very well. They are intimately related. And when we looked at the analysis without using those grid decarbonization projections, operational carbon impacts far exceeded embodied for a lot of these project types. So the electrification, yes, must happen. It has to happen at the exact same time as the grid decarbonizing in real ways. I would say that the fourth for concrete, steel, I would also throw in there like upfront emissions, structural systems in general. They get a lot of focus on like decarbonization design strategies in practice as well as policies, and rightly so, because they are really big contributors to embodied carbon. But what was clear when we did our contributions assessment is that those aren't the only things that matter, and they don't always matter to the same extent across building types. So some of the buildings that Yang pointed out actually had really significant emissions from some of these other scopes, elements, and life cycle stages that can be really important to analyze. So one of the key takeaways there was really designers and policymakers should really be seeking to include more scope, more life cycle stages into the assessments. One, to fully account for the true carbon impacts of buildings, but also to incentivize reduction of those other categories or things that aren't often modeled in current practices, where if you can exclude them entirely, there's really no incentive to reduce them. Fifth was that this is just really valuable information. We were able to, with relatively limited effort, our data contributors were able to send us this information for us to do some really exciting stuff with it. So this was all reflecting data that kind of exists in order to paint a picture of whole life carbon impacts. And second with that is, like I said before, it really starts to show that based on the different building types for a lot of different conditions and reasons, decarbonization strategies might change in really drastic ways from one building to the next. And that generally, like one blanket strategy or one prescriptive strategy isn't going to work for every single building, especially across different geographies that have different grids and different construction practices. And the last one, which I think Matt started to talk about a little bit at the beginning, is we don't know the full picture. There was lots of gaps. We had lots of limitations in this study. I think still we had some significant findings, and I think hopefully this is really helpful for everyone. But there are a lot of next steps and a lot of things we need to do to really make this a more holistic assessment of whole life carbon impacts. And so with that, I'll turn it to Matt.
Thanks, Brad. Yeah, like Brad said, with any scope of work that uses collected data from multiple different parties, there is quite a long list of limitations that go hand in hand with that type of data collection, manipulation, and use. That's not to discredit the results and conclusions and findings from this scope of work. It's just to highlight that there are certain things you can and cannot say about the results. That being said, some of the key limitations that we found from the study is the lack of verification of the provided embodied carbon operational energy use data that was provided by the data contributors. They had extensive documentation and guidance for how to do the assessments and what to look for and how to assess it. But there wasn't any third-party verification of the models or assumptions that were provided to us by the data contributors. Coupled with that, we used operational energy use values that were averaged out across an annual time frame. With buildings that integrate on-site energy generation and on-site energy storage, time of use factors become much more critical to take into consideration. And that's going to be one of the scopes of work that we're hoping to look into further about the granularity of operational energy use data. Biogenic carbon or sequestered carbon was not considered in this study. This is a huge thing to consider, especially for timber frame buildings or really any form of building that uses a lot of biogenic materials. The other physical scope aspects of the building that were not included on-site energy generation, on-site energy storage, as I previously said, mechanical, electrical, plumbing systems, site work, fixtures, furniture, and equipment, also known as FF&E. And then from the temporal scope, we did not include construction impacts, fugitive emissions, maintenance, repair, operational water use, user activities, nor deconstruction or module D impacts, which exist outside the system boundary for the study. Next slide, Brad. So what's really exciting about the scope of work is that it really highlights all of the fun, interesting, exciting things that we can look forward to and look into further to help everybody decarbonize the built environment. So some of the future research priorities that we feel are important include the estimation of the missing aspects of both the physical and temporal scope. We want to expand the scope of the study to be a broader geographic representation as well as broader building typology coverage. We focus mainly on commercial office, commercial non-office, multifamily residential, and a few other building typologies, but there's a lot more building typologies out there. Like I said previously, we want to include biogenic carbon within future studies, as well as provide reporting guidelines to industry, investigate the granularity of operational energy use, information for net zero energy and net zero carbon claims, because net zero energy doesn't necessarily mean net zero carbon. And we want to explore the embodied and operational impacts of retrofit, renovation, and reuse projects. And I'm going to hand it back to Brad to finish us off.
So yeah, where this is all heading, we're actually going to publish another version of this study, expand it, and convert it into an academic journal paper targeting submission later this year. For the larger benchmarking study, like I said, we're just kind of starting to kick off analysis on the rest of the data that we have. So our data collection effort has largely completed, but we do hope to continue collecting more in the future. And we're starting to analyze the sort of 250 plus-ish building projects we have across North America, and hopefully getting some more answers to some of the correlation challenges and maybe some clearer guidance on largest embodied carbon contributors and other trends. So on that front, there's a lot of different outputs that are going to come out in the next year or a little bit beyond, sort of a database methodology paper and a data set, some exploratory data analysis looking at some of those trends, like what are we seeing across this major set of buildings, and then an initial benchmarks and findings report, not too dissimilar from this one, but with a lot larger of a data set. And then finally, looking into the uncertainty and sensitivity of those results. What's really driving some of those variables, and how can we kind of visualize the level of error or the amount of uncertainty across this data. I think with that, we were just going to give like one last thought about our time working on this project, which has been really fun. We've had a lot of great discussions about it. And so I'll kick it over to Yang. Would you like to share something interesting or a thought that you had to close us off? And we'll all give one.
Yes, thanks, Brad. So I believe maybe most of the audience know that recently the White House released a document, the title like National Definition of the Zero Emission Buildings based on the operational energy part. And I believe that the second part, which is search about the embodied carbon, will be released in the future. So I'm happy to see finally we officially address this operational carbon and embodied carbon holistically and equally. And we know that to address this problem, whole life carbon assessments are really useful, important tool. But the concept of the whole life carbon still new and with lots of challenges. For example, compared with the traditional whole life building LCA, whole life carbon assessments add more uncertainty associated with the operational energy consumption. And also we need a more expanded physical scope, including the MEP and the interiors, especially associated with the trade-off, the problem, trade-off issues of operational carbon and embodied carbon. And there was also challenges about how can we find the best practice to assess the whole life carbon. There was some kind of issue considering associated with the choosing the best grid decarbonization scenarios and the operational energy consumption and the LCI background data sets. So there were lots of things to do in the future.
Yeah,
So
definitely.
I will pass. Maybe Brad, you want to go first?
Sure. Yeah, I think I spoke about one of them a little bit already, and I think it's important to recognize that when we set out to do this larger project, we never really asked people to send us whole life carbon models or whole life carbon results. We identified that there are sources of information available that could enable us to get that information together and do our own assessments of whole life carbon. So what our data contributors actually sent us was mostly existing LCAs and existing energy model results that they already had conducted for various purposes. So one, that's really exciting, just thinking about like what already exists in relatively common industry practices. Like what we've done here is a pretty cool analysis and shows what could be done with that information that designers and practitioners are already generating. And the other thing that kind of builds off that I'm really excited about is the kind of momentum and energy towards pushing towards standardization for whole life carbon modeling. So the development of the RICS standard in the UK, as well as the ICC ASHRAE 240P standard in North America, are both kind of pushing to address a lot of the concerns and limitations and gaps of this study. And they're kind of coming out at a perfect time in order to build that more rigorous modeling quality within practices in order to really scale what we're able to do with this data, which is really exciting. So I think what's happening is already really great. And if folks or policymakers on the call, if they're like, well, what do I do? I mean, this is a really great example of what could be done with information that already exists. And I think looking forward, I would highly advocate for tracking some of these new standards and guidance documents to really elevate this type of analysis or this type of policy development or design practice, et cetera, to a more rigorous level. Matt, how about you?
Awesome. I love this kind of stuff. I had so much fun working on this project, especially with you guys, like Brad and Yang. It was really fun and interesting to see what kinds of stuff we could say based off the data that we collected and what was available to us. And then on the other side of it, from talking with people in industry, the amount of drive and initiative and focus being put on this, especially in the past few years, is absolutely incredible to see. I've done quite a few speaking engagements, and I got a few people in one of the last ones that I said, if one firm wins climate change, we still all lose. And I think that point holds true to the kinds of collaboration and engagement that everybody wants to have in this area, because everybody is wanting to learn from each other and is recognizing that we don't have all the right answers right now and we don't have all the right solutions. But if we're able to collaborate and support one another, then we can all shift towards a decarbonized built environment and also raise the bar for what the base level of knowledge is to allow everybody to engage in conversations of sustainability and low impact design right from the start of the design process. And that has been absolutely incredible to see.
I would second that as well. All right, with that, I'm going to stop our recording and we'll open it up for some Q&A. Thank you all very much.